In fact, most won't even consider looking at alternatives. But wind power can be a valuable addition to many self-sufficient setups. Today, when we talk about wind power, we are shown 300-foot industrial giants owned by multi-billion-dollar utilities. We are told that home wind is a hobbyist distraction, while we are ushered towards solar panels that require a massive footprint and a 20-year debt cycle. But the physics of wind shouldn't be underestimated. A single cubic yard of air moving at 20 miles per hour contains far more energy density than the photons hitting a solar panel of the same size. I'm about to share 6 turbines that represent the cutting edge of off-grid wind technology that you can utilize in your own off-grid system, all designed to overcome the biggest problems in small-scale wind energy. I'll break each of them down by cost, efficiency, and what makes these some of the most innovative projects in off-grid energy right now. Number 6. Tesup Atlas. One of the biggest hurdles to home wind power is the tower. Most local building codes or homeowners associations treat a 60-foot mast as an eyesore or a zoning violation. It is a form of passive suppression. If you can't get a turbine high enough to reach the smooth, high-velocity air, traditional setups won't work, and you stay trapped on the grid. But you don't need to build a massive tower if you change the geometry of how you catch the wind. Enter the Tesup Atlas. The Atlas is a vertical-axis wind turbine engineered specifically to bypass strict zoning laws and solve the unique challenges of residential environments, all while keeping capital costs realistic for a home installation. In a standard neighborhood, houses, fences, and trees chop up the passing air, creating highly turbulent, unpredictable gusts. Traditional horizontal wind blades have to constantly rotate their entire body to face the wind, losing massive amounts of efficiency every single time the direction shifts. The Atlas, on the other hand, doesn't care which way the wind blows. Because its aluminum scoops loop vertically around a central axis, it features a 360-degree catchment area. It captures kinetic energy from any direction simultaneously, allowing it to thrive on the chaotic, swirling air currents found right around your roofline. But the real engineering breakthrough here is how it handles structural physics, which translates directly to major financial savings. When you mount a traditional horizontal propeller to a building, the uneven aerodynamic forces create massive lateral sway, low-frequency humming, and dynamic vibrations that travel down into the walls. Fixing that usually requires hiring a structural engineer and spending thousands on building reinforcement. The Atlas avoids this completely. Because it spins on a perfectly balanced vertical axis, all mechanical forces are channeled straight down through its center of gravity. There is no rhythmic buffeting, nor are there any low-frequency vibrations, and it operates with minimal noise, meaning it can be bolted directly to a standard roof beam or a simple ground pole. Financially, this system changes the math on residential wind. A heavy-duty, entry-level version of the Atlas core generator starts at a very modest $900 with complete modular kits including custom blade profiles and advanced charge controllers averaging between $1,500 and $3,000. In terms of power, the Atlas core features an integrated IoT generator capable of producing up to a massive 10 kilowatts of raw potential energy, which manages daily electricity production through a built-in controller. The unit starts rotating at wind speeds of just 9 miles per hour and can be retrofitted with specialized low-wind blades that drop that starting speed down to 7 miles per hour. Because it requires absolutely no extra land, invisible to your neighbor's line of sight, and keeps installation costs to a fraction of a commercial-scale architectural setup, it turns a strict zoning problem into a highly accessible energy solution. It proves that you don't need a 60-foot tower or a second mortgage to harvest the sky. You just need a smarter piece of geometry. Number 5. windenergy SD6. If you look at most modern wind turbines, they are shockingly fragile. They rely on complex wind sensors, electric motors to turn them into the wind, and active digital braking systems to keep them from spinning apart in a storm. In engineering, complexity is the absolute enemy of self-sufficiency. If a motherboard fries during a blizzard, your power is gone, and all you're left with is an expensive maintenance bill. The SD6, designed by windenergy in Scotland, is the absolute antithesis of that fragile complexity. It is a 6 kilowatt powerhouse that rejects computerized automation in favor of heavy-duty, passive, mechanical engineering. Most traditional turbines face directly into the wind. The SD6 reverses this geometry, using a downwind architecture where the wind actually passes the tower before hitting the blades. Because of this, it doesn't need a motorized tail vane or a computer chip to find the air current. The natural force of the wind pulls the turbine into the correct orientation entirely on its own, like a heavy-duty weather vane. But the real engineering genius lies in its ability to handle a storm. During high-velocity gales, conventional turbines have to engage emergency brakes and shut down completely to prevent structural failure. But the SD6 doesn't shut down. It features a purely mechanical centrifugal force system called the delta rotor. As wind speeds accelerate, the physical force causes the thermoplastic composite blades to automatically twist, changing their mechanical pitch. By pitching backwards, they naturally shed excess wind force, allowing the turbine to continuously generate power safely in extreme gales, while other systems are forced to freeze. Financially, the SD6 is no small investment. It is a serious, utility-scale piece of technology for your property. The turbine hardware, combined with a heavy-duty $9,800 hydraulic monopole tower and a professional concrete foundation pour, brings the total installed cost into the $25,000 to $35,000 range. And that sounds like a lot, and it is, but the payoff is pure, raw energy density. Armed with a massive 19-foot diameter rotor, the SD6 thrives on sites with modest average wind speeds of around 12 miles per hour, generating an incredible 10,000 to 14,000 kilowatt hours of electricity per year. Given that the average home consumes roughly 10,600 kilowatt hours annually, this single machine possesses the power to completely zero out your utility bill. Furthermore, the lack of digital components drastically alters its long-term operating economics. Free from sensor-rich electronics, the turbine is built to last 25 years without a major overhaul, requiring just a brief annual manual inspection and a standard bearing replacement every 5 to 7 years. It is heavy, uncompromising engineering. But once the concrete cures and the tower tilts up, it acts as a permanent sentinel on your property, working while you sleep, and working hardest when the winter storms roll in and the sun refuses to shine. Next up, we have the Liam F1. Developed in 2014 by Dutch inventor Marinus Miramet, this design uses the principles of an Archimedes screw to solve many of the common problems that have plagued small-scale wind projects for decades. In open countryside, the wind moves in laminar flow, the steady, uninterrupted air pattern that conventional propellers were designed to harvest. But the moment you bring a propeller into a city, a suburb, or a wooded property, that smoothness collapses. The air ricochets off buildings, trees, and roof lines, arriving at the rotor as a swirling, gusting mess that changes direction every few seconds. A horizontal axis propeller has to yaw its entire body to chase that shifting wind, and every degree of misalignment robs it of efficiency. But for this turbine, its conical spiral accepts incoming air at angles of up to 60 degrees off-axis without losing performance, and the cone itself yaws into the wind automatically without the use of sensors or electric motors. The clever geometry finds its own orientation through pure physics. But the real engineering benefit happens when the air reaches the rotor. As the spiral catches the moving wind, it draws the air into the geometry, redirects it 90 degrees, and slows it to nearly zero by the time it exits the back of the rotor. The result is a turbine that runs a lot quieter than the conventional design. A 3-blade propeller on a residential roof operates somewhere between 55 and 65 decibels, a level comparable to a running dishwasher. But the Liam F1 operates below 45 decibels, quieter than a household refrigerator. Some residents have even reported standing directly underneath the operating rotor in a strong wind and hearing nothing beyond the natural rush of the air itself. Its clever geometry makes it quieter and more adaptable to unpredictable wind conditions, but it also makes it extremely efficient at extracting kinetic energy. The manufacturer claims that the spiral extracts up to 80% of the theoretical maximum available in the wind, a figure known as the Betz limit. Financially, the Liam F1 sits at the premium end of the residential market. The 1.5 kilowatt turbine runs around $3,200, and a fully installed system, controller, dump load, mounting hardware, and wiring typically lands between $5,000 and $7,000. Number 3. Flower turbines. The third innovation on my list addresses the two most common complaints about residential wind power: the disruptive noise and the danger of bird strikes. Standard propeller turbines, known as horizontal axis wind turbines, feature blade tips that move at 5 to 7 times the speed of the passing wind. This hypervelocity slicing of the air creates a high-pitched, rhythmic whoosh that can resonate across a neighborhood. But the flower turbines, based in the Netherlands and the United States, solves this entirely by utilizing a vertical axis design that looks more like an aerodynamic tulip than a traditional windmill. Because the curved aluminum blades loop vertically around a central shaft, they move at a much lower tip speed ratio. This geometry renders them effectively silent, producing a low-frequency hum that is completely masked by ambient suburban noise. You can stand directly next to one and have a normal conversation. But the real engineering secret here isn't just the silence. It's a direct defiance of traditional aerodynamics regarding how they behave in groups. Standard propellers create a massive wake of highly turbulent, dirty air behind them. If you put two traditional turbines close together, the second one will suffer a massive drop in efficiency because it is choking on the chaotic wake of the first. But flower turbines exploit the exact opposite effect. Through a fluid dynamics phenomenon called the cluster effect, placing these turbines tight together actually increases their individual performance by up to 20%. The swirling air shed by the rotation of one turbine acts as a mechanical gear, actively pushing and accelerating the blades of the neighboring unit. This behavior allows you to create a high-density, modular garden of power in a small backyard or across a flat commercial roofline. They are also entirely bird-safe, because the vertical scoops form a distinct, solid, cylindrical silhouette when spinning. Animals see them as an obstacle to avoid, rather than an invisible blur of deadly blade tips. Economically, flower turbines are structured as highly scalable, modular consumer tech assets rather than massive capital overhauls. A small, entry-level turbine stands at about 3 feet tall and starts at roughly $1,400, making it perfect for charging small, off-grid battery banks. The mid-range versions, designed for residential rooftops, start around $4,500, while their largest, commercial-grade vertical units can cost up to $9,500. The true financial payoff, however, comes from their hyper-low starting threshold. While industrial giants don't even wake up until wind speeds hit 7 or 8 miles per hour, flower turbines begin generating usable electricity at speeds as low as 2 miles per hour. Because gentle 2 to 5 mile per hour breezes happen far more frequently in urban environments than high-speed gales, these turbines continuously trickle power into your system throughout the day. By taking advantage of the cluster effect, an investment in a small matrix of 3 or 4 mid-sized units doesn't just multiply your power linearly. It creates an interconnected, highly efficient microgrid that squeezes maximum electrical output out of the tightest residential footprints. Number 2. Primus wind power. Sometimes, true innovation isn't about creating a bizarre new shape. It's about the relentless refinement of a proven tool. Primus wind power, operating out of Colorado, produces the Air series of turbines. These are compact, micro-scale machines rated at 400 watts. To someone accustomed to the massive scale of the centralized commercial grid, 400 watts might sound like a toy. But this is where understanding a baseline energy load changes the math. A 400-watt turbine running consistently through a dark, windy night provides the continuous baseline energy required to power a highly efficient property, keeping refrigeration online, running LED lighting arrays, and maintaining vital communication systems when solar panels are completely blind. The Air series was originally engineered for the brutal maritime industry, meaning its physical architecture was built from the ground up to survive corrosive salt spray, sub-zero ocean winds, and constant structural vibrations on the mast of a sailboat. The body is cast from aircraft-grade aluminum, and the specialized blades are molded from a carbon fiber reinforced composite designed to flex rather than snap under high aerodynamic loads. Mechanically, the system embraces extreme minimalism. The only moving part on the entire machine is the rotor itself. But the real engineering disruption here is the internal regulator. Historically, installing small-scale wind power required a complex, wall-sized cabinet of secondary electronics, including external rectifiers, dump loads, and heavy charge controllers, just to safely manage battery charging without frying the system. The Primus engineering team miniaturized all of that infrastructure and built the electronic brains directly into the rotating nacelle of the turbine itself. You don't need a degree in electrical engineering to wire it up. You simply run 2 standard copper wires down your mounting pole, and they connect straight into your battery bank. Financially, the Primus Air Series represents the ultimate entry-level gateway into wind independence. The entire self-contained turbine unit generally costs between $1,200 and $1,500. And because it requires no complex external controller cabinets, your secondary hardware costs are practically non-existent. In terms of real-world energy output, the machine features a hyper-low startup wind speed, with the carbon blades beginning to spin at just 7 miles per hour. Once the wind hits a steady 12 miles per hour, a single unit will consistently generate around 30 to 35 kilowatt-hours of electricity per month. It is the definitive plug-and-play microgenerator of the wind world. For a cabin, a mobile tiny house, or an emergency off-grid backup system, it provides a level of rugged, low-cost simplicity that the multi-billion-dollar utility industry claims is impossible to achieve. Number 1. The IceWind. The final turbine on our list looks to address the problem of too much wind. In environments like Iceland, the Great Plains, or high-altitude mountain ridges, the wind doesn't just blow, it screams. Most residential turbines have a strict, fragile survival speed. If a storm rolls in and the wind hits 100 miles per hour, traditional blades will experience catastrophic structural failure and be completely destroyed. The IceWind turbine, engineered by an innovative design team in Iceland, reverses this limitation by creating a vertical axis machine built specifically to thrive in these otherwise unsurvivable conditions. The secret to its engineering is a highly sophisticated dual-blade geometry. The core of the machine features a Savonius-style inner rotor, which acts like a series of heavy scoops to deliver massive mechanical torque and allow the system to wake up and start spinning in ultra-low winds. Wrapping around that core is an outer, aerodynamic Darius-style blade system that takes over at higher speeds to maximize aerodynamic efficiency. By combining these 2 distinct aerodynamic profiles, the IceWind doesn't experience the typical structural stress of horizontal propellers. It is forged from marine-grade stainless steel, aircraft aluminum, and carbon fiber, allowing it to withstand relentless, punishing wind speeds of up to 130 miles per hour without flexing or braking. Furthermore, the physical architecture is completely sealed. Traditional windmills house their sensitive gearboxes and electronics high up in the air, where they are exposed to freezing rain and dust. The IceWind places its heavy direct-drive generator at the absolute base of the unit, completely enclosed and protected from the elements. There are no exposed gears, no external wiring, and no mechanical micro-switches to freeze over. It operates as a silent, indestructible monolith that continuously converts kinetic energy into electricity in conditions that would shatter a conventional windmill to pieces. From an economic perspective, the IceWind is built as a premium, extreme weather asset. The residential and off-grid models, like the Freya series, generally range between $3,200 and $4,500, depending on the specific generator output configuration. While it generates a modest 150 to 300 watts of continuous power, depending on the model scale, the financial calculation here isn't based on raw bulk volume, it is based on absolute reliability. Because the generator is direct drive and lacks a complex mechanical transmission, it boasts an incredible 25-year operational lifespan with practically zero maintenance costs. It requires no annual greasing, no electronic calibration, and can be mounted directly to an existing pole, a concrete pad, or a remote telecom tower. It is the ultimate set-it-and-forget-it energy tool for the most rugged environments on Earth. It proves that when nature throws its worst at you, you don't need to shut down your system. You just need tech tough enough to stand its ground. While the entire world rushes to cover their roofs in solar panels, many self-generators miss a fundamental law of physics. Wind has a vastly higher kinetic energy density than solar. Solar relies on capturing fleeting photons across a flat surface, but wind is a 3-dimensional volume of moving force. A single compact turbine running through a dark winter storm can produce more raw energy in 24 hours than an entire residential solar array can generate in a week. If your goal is true energy independence, wind isn't just a secondary option, it is the ultimate equalizer. But achieving that independence requires moving away from guesswork and grounding your setup in practical data. Your first definitive step is measuring the invisible resource above your head. You cannot guess your wind speed. Investing less than $100 in a digital data logging anemometer and mounting it at your intended installation height changes everything. By leaving that anemometer in place to log data for 6 to 12 months, you will map out your property's exact wind seasonality. If the data shows an average annual wind speed of less than 8 or 9 miles per hour, wind generation might not be the primary driver for your property. But if your local wind speeds are strong, the economics of your entire energy ecosystem shift. This is where wind reveals its true superpower as the perfect structural partner to solar. In the dead of winter, when the sun hangs low, the days are brief, and solar panels are at their weakest. Global wind currents are typically at their absolute strongest. By integrating an option like the Primus Air or a modular cluster of flower turbines into an existing off-grid solar system, you can reduce your expensive chemical battery storage requirements by up to 40%. Instead of buying thousands of dollars in extra lithium batteries to store power for a rainy day, you are letting the wind naturally fill the gaps in real time, working the night shift while your solar panels sleep. And you no longer have to build a giant, industrialized tower to do it. Whether you leverage the 360-degree urban geometry of the Tesup Atlas to bypass strict zoning laws, or deploy an indestructible sentinel like the SD6 to handle severe open-plain gales, modern engineering has brought wind power down to a human scale. These systems turn strict local building codes from a barrier into a design parameter. Wind was the very first free fuel humanity ever harnessed to cross vast oceans and grind grain. It hasn't gone anywhere. The 200 trillion kilowatts of kinetic energy spinning through the Earth's atmosphere passes over your roof every single day, completely free of charge. If you believe that the air above your head should be an asset rather than a nuisance, and if you want to stop renting your life from a centralized utility grid, then the technology to harvest the sky is finally in your hands. If you are interested in achieving energy independence and would like to know how else you can achieve that, then you may also be interested in our video on Pico, Hydro, an endless energy supply you can build yourself for just $50.